Hi guys, welcome to the Support Vector Machines lecture. In this lecture, we will talk about another widely used supervised machine learning technique, support vector machines, also known as SVMs. SVMs deliver state-of-the-art performance in a range of real-world applications and considered as one of the standard tools for machine learning. We will explore the theory behind SVMs and try to understand their working principle with practical examples. Support vector machines, or SVMs, are actually the set of supervised learning methods used for both classification and regression analysis. SVMs have been shown to perform well in a variety of settings and are often considered one of the best out-of-the-box classifiers for data scientists. Consider we are given with a set of training samples, each marked as belonging to one or the other of two categories or classes. SVM training algorithms build a model that assigns new examples, which are our test data points, to one class or category or to the other, making it non-probabilistic binary linear classifier. Support vector machine model is a representation of the examples as points in n-dimensional space, where n is the number of features, mapped so that the examples of the separate categories are divided by a clear gap that is as wide as possible. We will talk about this gap in the coming slides and how we can get this type of gaps. Moving forward, new examples or the test data points are then mapped into the same n-dimensional space, and predictions are made for a category based on which side of the gap the new example or the test data point falls. Let's try to understand this process with some training dataset. Consider we have a labeled training data, in this example blue and green, with some features, feature 1 and feature 2. We want to predict the class for our new point in this binary classification problem. If we want to draw hyperplanes, which are simple lines in this two-dimensional data, to separate these two classes perfectly, we have lots of options like A, B, and C in this diagram. Our question is, which plane is the best to select? If we recall our previous slide, we said the plane which maximizes the margin between the classes is the best option. In this case, C plane is separating with maximum margin. So we are going to select C as a best option. A and B also separate the classes, but only with the small margin. Let's consider C only and remove A and B. In this diagram now, we have the dotted lines, which are the margin lines that extend out from the hyperplane C. The vector points or the training data points in red circles that are touching these dotted lines are called support vectors. And this is where the name support vector machines comes from. So now we have seen that we can separate these two classes in this linear classification type of problem using a simple line between these two classes, which is actually maximizing the margin. SVM is great actually. In addition to performing linear classification, SVM can efficiently perform nonlinear classification using what is called the kernel trick, which is implicitly mapping these features into higher dimensional feature space. Like in this data set, we can clearly see two separate classes, but we can't use a linear classifier or simple straight line to separate these two classes. This is where the kernel trick does its job. So in the figure shown on our right side, if we represent the same data on our left side into a higher dimensional feature space, now it is easily separable by a plane shown by lighter color. So the kernel trick transforms the data in a feature space where the instances from the two classes may be linearly separable. So just an overview on the SVM's kernel trick. We got the data which was not linearly separable. Using the kernel trick, we end up separating the non-linearly separable data by viewing in high dimensional feature space. So far, this was all about the theory behind SVMs. In this lecture, we have covered the key points and principle behind SVMs. Let's learn by doing and see how the things actually work in reality. In the next lecture, we will explore the breast cancer dataset using SVMs. In this way, we will also be able to compare and see the differences between the other algorithms that we have trained and deployed on the same dataset. See you in the next lecture. Good luck.